Dr. Li Hui is an engineer, academic, and an entrepreneur. She is a recipient of the Chinese National Distinguished Expert Award and a Class A tenant under Shenzhen Court Plan. Previously, she served as a technical lead at the Fuel Cell Innovation Institute of Canada's National Research Council, where she spearheaded multiple international hydrogen energy projects and groundbreaking achievement important change purpose fuel cell. In 2021, she founded a company called BriHyNergy. BriHyNergy Shenzhen Company Limited, leading her team to overcome critical bottleneck in key material and components for PEM water electrolysis. Ladies and gentlemen, please welcome our next speaker, Dr. Li Hui.
Thank you for your introduction, and thank you for the audience staying here listening to me. Yeah, good. Thank you. Thank you. Okay. Thank you for the introduction. My name is Hui Li. I'm actually also a academic. I'm chair professor still in University of Science and Technology. But today I'm mainly reporting my achievements and advances of the company that I've founded. So from several aspects, first of all, industrial overview. Comparing a few technologies and what is PEM system. And I think previous speakers touched on the comparison of different hydrogen technologies, but here I like to compare a little bit more. I mean, the strategic importance of hydrogen as energy storage has been consensus, and particularly recently it was reinforced by the central government writing it into the national energy law. But I think the key challenge is the economic viability, which requires dramatic reduction of the hydrogen production cost. So that's why a lot of people, including myself, have been working on this area. I mean, if this here, I only list 3 key technologies. One is ALK. I think everyone is very familiar with this one. But just for comparison, the key advantages of the alkaline ALK is its mature supply chain and the low cost, of course. But the drawback is the safety problem issue when it is not very well handled because of the porous material, the diaphragm in the middle. So, but on the contrary, PEM is very different. The beauty of PEM is that the fast response and the higher safety, and so that's why it has a better compatibility with the renewable energy, I mean the fluctuation. And more importantly, it can be tackled in combination with other technologies. But of course, the biggest challenge is to reduce the cost of PEM. So that's why what we have been doing on this one. But a lot of buzz in the last year about the AEM, anion exchange membrane technology. I was often asked whether it is mature, why it was so popular, so hot last year. If you look at the technology readiness level on the very top end of the square, if you look at ALK, it is about 9 to 10 or maybe 8 to 9 roughly, depending on the maturity of the technology, the supply chain. But PEM is around 8 to 7. But AEM is only around 2 to 3. That's how I read it. It really depends on the maturity of the technology. And so it's basically an AEM emerging technology. And often we were asked whether PEM is going to completely replace ALK or whether AEM is going to be the future. So that's a very difficult question to answer. But to me, my insight is that in the near-term future, or maybe in the long-term future, there's always a hybrid scenario. I mean, depending on the scenarios, if you look at the y-axis, from the bottom to up is the gigawatt scale, and in the middle is a megawatt scale. On the top is the rooftop or microgrid, it's a smaller scale. And on the x-axis is the time elapsed. So really, really different situations, the scenarios can be different. I mean, for example, in China, which is in last 2 years, the major deployment, I mean, 90% is ALK. The reason being that in China, the scenario is mostly gigawatt scale. And of course, the CapEx matters a lot. So that's why the deployment is mostly dominated by ALK. But if you look at the landscape of Europe, the dominance technology, I mean, split between ALK and the PEM. I mean, PEM in Europe is more than 50% because in 2011, Germany has defined the PEM as a standardized solution for connecting to renewable energy. So that's why really depending on the area that you're talking about. So, but in my view, in the future, depending on the cost and depending on the scenarios, the best way is a hybrid solution that integrate all technologies into one system that optimize the LOCH. But the problem right now, the challenge is the control. We don't have a good control. And also we don't really have a lot of data. For example, even though the deployment of last year in China is like how many gigawatts, but still they are very separated, isolated applications. For example, Kuching 1. There are piles of ALK electrolyzers, but you don't really have a centralized controlled system. So we are still at the learning stage. So this is a future in my brain. So it's going to be not one with or the other. It's a hybrid. Now let's focus on the PEM technology. I mean, if you look at the PEM electrolyzer system, the heart of the electrolyzer is a stack. But if you look at the bottom of the stack, in the middle is a proton exchange membrane. On the sides of two sides of it is the catalyst coated. I mean, the 3-layer we call MEA, membrane electrode assembly. And this MEA is the key driver for performance and the cost, accounting about 40% of the total cost of the stack. So that's why it comes to the introduction of the BriHyNergy, the company. So BriHyNergy was established in 2021. We majorly focus on the PEM electrolyzer, trying to unlock the challenges, particularly the cost, to unleash its potential for renewable energy. Of course, we also do AEM because of the team structure. AEM, we started to transition AEM last year from the lab scale to early demo scale because of the demand of the industry. Our past investors include ATL, Innovation, Sequoia China, and so on. I mean, this too busy slides. I just wanted to say that I came back from Canada in 2015, and so I worked on hydrogen for about 15 years before coming back. And since coming back to China, I built my team on the university. So we established the company in 2021, but the IP was accumulated between 2015 and 2021. So we have achieved a lot of milestones over the years before coming back to China and after coming back to China. So I wanted to mention the R&D platform that I have on the campus. I think I'm very proud that I always have had at least about 30 to 40 R&D members in my team on the campus. So that was the early stage of the technology in the company. So that's why if you look at the share structure, you see SUSTAC as a stakeholder. So that's how it works in our campus. So this R&D center really builds a lot of technology from there. And if you look at the product portfolio of our company, on PEM, we are the only private company in China that strategically developing the core membrane as a cornerstone, or maybe as a foundational technology, to span our product to MEA and then to stack. So that gives us very unique position that we are competitive not only in the performance of the products, but also cost-wise. But for MEA, the scope is very different. We started from the polymer design and polymer synthesis and the membrane and MEA and the stacks. But of course, the structures of the two systems are very similar in terms of the stack design, so we can borrow from each other. It's just that the membrane materials are different, the catalyst materials are different, but the stack design are very similar. So, and product portfolio, I wanted to focus a little bit more on the product. First of all, it's a core material. That's what I said, the cornerstone for our company. We developed a dual-enhanced proton exchange membrane. I call it game changer. If you look at the price drop for last year, you can notice that the PEM has dropped by 50%. I mean, of course, the reduction of iridium, precious metal loading has contributed some, but mostly it is the membrane that contributes the reduction, because the membrane, comparing to the traditional Nafion two-bond membrane, which is 180 thick, our membrane is only 80. So the conductivity is very low. And then instead of using about 200 cells for a 1 megawatt, you only need to use 100. That's just a rough number. So that's why the cost of the PEM dropped significantly in last year. So we call it a game changer. We actually right now, because it's becoming thinner, we use mechanical and chemical reinforcement. And so that's why we have this membrane. You may be asking whether it is durable. We did a lot of characterization testing. For example, in this figure, the lifetime for 5,000 hours, you don't really see a big degradation. So that tells you how good the membrane is. And the other one is MEA. The MEA, we call high performance and long life MEA, was developed and scaled under the Chinese, the 14th five-year plan program. I was a technical leader, a 5-year program, couple of million, $20 million program under the national program. Because of that good performance, long-lasting MEA. Right now we have several products. It can be customized. Look at the three figures on the bottom. There are 3 core performance metrics. IV curve, the other one is hydrogen content in the oxygen. The other one is the degradation rate under the fluctuated power. These 3 figures tell you the same thing. In conclusion, among the 3 metrics, they're all at the leading position in, domestically, and some of them globally. And the last one platform is the stacks. We have developed 4 different platforms ranging from very small 1 cubic meter per hour stack to bigger ones. For example, the bigger one is the R platform. It can span from 1 megawatts to 3 megawatts, which is 200 to 600 nomical cubic meter per hour in a single stack. This is one of the biggest one, because the bigger you go, the more cost-effective it is. So that's our stack technologies. Those are just the parameters for the stack. I just quickly go through because we have different platforms for different applications, particularly for in Europe, for refueling stations, PEM is particularly suitable because you have the demand of fluctuation from the solar and wind. You also have the demand from the hydrogen tank because you may run out of hydrogen because of fueling of the fuel cell trucks or vehicles, and then your electrolyzer system has to respond quickly. So that requires fast reaction, so which make PEM suitable for that purpose. So that's why in Europe, a lot of 1 megawatt or 2 megawatt system for refueling stations. And those are the smaller ones for semiconductor or for fossil fuel power cooling purpose. And lastly, in PEM, we have collaborations with our key partners to make a couple of standardized final turnkey solution. We have like 1,000 cubic meter solution. That is 1 BOP connecting with 2 501, or 1 BOP connecting with 4 250. So that has been our standard solution for the system-wise. For AEM, we actually started very, very early from my co-founder. When he worked in Canada, his major has been organic chemistry, particularly in anion exchange membrane. I mean, this paper shows you the very famous company in Vancouver. The key technology was actually invented by him. That's why you see his name on the first for a couple of the citations there. And the right top figure shows you the comparison of our own membrane with very typical commercial products like E60. It's not too nice to mention their names, but that's what we compare. On the left-hand side, you can see our kilogram scale polymerization reactor. And on the right-hand bottom side, we can share the same membrane production line with our PEM. So we are very ready when the time comes, but I don't think AEM is ready yet for massive application. Because as far as I know, on the market side, there has no company that has passed 1,000-hour test in the real stack AEM so far. It's just too short, the lifetime. This one shows you the capabilities that we have for fluid simulation mechanics, and it's very similar to PEM electrolyzer, but the right-hand bottom one is a real stack that we did for a Sinopec project. And lastly, I'm proudly showing you the production lines that we have, because for a company, particularly for a company funded by me like a professor, and the investors or clients are always doubtful about our engineering capability. But I think we did pretty well in the production line design, production line execution, and the production. For example, in our manufacturing system, we have very rigid quality control system. We have system certification, ISO, and so on. And just to show you, we have, if not the first one, but at the very first, one of the very first few IME production lines in China, global as well, 4 gigawatts equivalent. For MEA, we also have a production line. If one of you have time to visit Shenzhen, please welcome to our company to see the production lines there. We also have another third line, is the stack assembly line. That is 1 gigawatt equivalent. They're all in operation right now. So lastly, project delivered. Domestically, we have delivered a 3 megawatts system in 2023. It's been operating, pretty impressive. Also, for European market. And we also won the project under 国家能源集团 and also shortlisted to the procurement layout for 中能建 twice. And future plan, we have very clear roadmap for cost reduction. I believe in the near future, you can have less than $20,000 per 1,000 nomic cubic meter for PEM. Lastly, going global. So BriHyNergy is the pioneer in securing the US ASME, Europe CE, and ISO 27443, the certificates for going global. Without those certificates, you just have a lot of barriers you just can't get into. So that's why we recently secured the order of 3 megawatts from European company. And that concludes my presentation. Hopefully I don't go over time. Thank you.
Thank you, Dr. Lee.